Hello viewers and welcome to another episode of Space Science with Python. Viewers, I changed a little bit the format of today's video and also the next times. Maybe you can write whether it's now a little bit better or not. I will shorten the videos a little bit because I was thinking, well, the good tutorials like online tutorials where you read or also some video tutorials, most code is already done and somebody else is explaining what has been done. And with some markdown recipes and with some comments, it's a little bit maybe easier to follow such a YouTube video. So I changed the format a little bit. I will just show what I coded and I will explain it cell by cell. So in the description part below, you see all the timestamps, and the timestamps correspond to the cells that are in this Jupyter notebook, and that is also available on my GitHub repository as always. Now, today we will talk a little bit about autoencoders. So last time we had some introduction into the theory of autoencoders. So a small recap, an autoencoder maps the input to the output. So it's basically like, yeah, the identity. Yeah, so the number one becomes the number one, in image of a dog becomes the image of a dog, and so on. But that's not 100% the truth, or yeah, actually it is. But the architecture of an autoencoder is, yeah, structured like a bottleneck, so to speak. So the information is being compressed to the center of the neural network, and then afterwards this compressed information is decoded to the original image. And so what the autoencoder or the deep learning architecture tries to do is it tries to learn some kind of low-dimensional representation of the input. So for example, an image of a dog or image of a cat is then some kind of vector in a small latent space. And that way, for example, you can denoise images because, yeah, images maybe not, noise is not really, yeah, relevant information. It's not highly correlated to anything in the image. So it's, yeah, being evaporated. Or you can also use the latent space for clustering purposes, for example. And this is what we will do. We will do some clustering on the data on our asteroid spectra. But before we do some clustering, I would suggest to build up a small autoencoder and go a little bit through the architecture. So I also wrote down here some markdown recipes. What we will do today, we will compress a 49-dimensional spectrum. Yeah, so it was like 49 features per asteroid. Yeah, and one step is the reflectance, the relative reflectance for a particular wavelength. We will compress it to 2 dimensions. And you will say, okay, a compression of 25, it's quite ambitious, and it is. It's nothing you can use maybe for production code or something. It's a little bit, I would say it's ridiculously extreme compression. But for our purpose, this 2-dimensional compression is something, yeah, that we will use for visualization. Yeah, it's simple as that. So we will not use we will not use it for clustering. So for clustering, we will use a higher dimensional thing in our in a future video. But a 2-dimensional space is quite nice to see some effects. Let's start with the coding. We have here our cell number 1 with all important libraries that we will use today and also in the next session. And in cell number 2, we set some NumPy and TensorFlow seeds. Now, what are these seeds all about? Well, for example, the weights of a neural network, they are somehow randomly initialized, right? And I was thinking maybe, well, having always the same initial weights would be nice to have some kind of reproducible results. So you see the same results as I do. So the weights of my notebook are always the same. So you can reproduce everything and you will not maybe get stuck and think, for me, it looks a little bit different. So to really stick with, let's say, static random values, we will use the seeding. Now, if you want to randomize everything, of course, you can comment out these 2 lines, 2 and 3. Now in command 3, we go now and do our standard stuff. As always, we are reading in our data from G Drive. So the data, the level 2 data, we generated in our previous videos here in line 11. And in line 14 to 16, we are assigning the reflectance spectra to an array, as well as the classes of the main group and also the bus class. Now the bus class is something we will not use today, but yeah, we will use it next time. But let's already have it here in cell number 3. We are doing also some kind of random shuffling split. Well, we will not have a classification problem, so it's maybe not really important to have the same test, or to preserve the class distribution of our training and test data. But still, I would suggest to do this here in cell 4 because still our neural network should train on some kind of class distribution that is, that also that is also present in the training data. And of course, our scaling. Our scaling here in cell number 5 is now today being done with the standard scaler here in row 6 from Scikit-Learn. And why do we do this? Well, we are putting our scaled training spectra here in line 9 into our neural network. But later we would also like to see the result, so the reconstructed signal. And to get the reconstructed signal, we have to retransform it or make the so-called inverse transformation to get the actual spectrum and not some kind of scaled thingy that we are training our neural network with. So we will keep the scaler here. We trained it now with our training data, or scale it with our training data, and then we are also transforming our test data as well. Okay, very good. The next cell here is a little bit huge. It's cell number 6, where we are creating our autoencoder. And let's go through it step by step. First of all, we need, of course, our input dimensionality of our spectra. So it's 49 features. And our dimensionality of our bottleneck should be 2. So I just set this here as a variable. Our neural network itself, our autoencoder, is defined in the function createModel, where we have our input layer and then 2 convolutional or convolutional 1D layers. You see, this time we are not using Keras tuner like in our previous video to improve our hyperparameters. This may be something for you to play around with, so feel free to use also Keras tuner for this task here. And you see also we are not using max pooling layers because we have an odd number of features and I don't want to remove any information, so I will stick with the convolutional 1D and then afterwards directly add a second 1D with 32 filters, and the first one has 16. Kernel size of both is 3. Now here we are now creating our bottleneck layer, so we encode it finally, and for this purpose we have to flatten our convolutional layer, and then we are creating a dense layer here in row 23 where we put the dimensionality of 2 in this argument here. So we have now a 2D layer, or a layer that returns 2 values, and hopefully these 2 values will represent our different spectra types. What we need to do now is we need to retransform it back, so we have to go to we have to go again with some kind of convolutional layer, but it's the little bit the other way around. It's called the transpose convolutional layer, so it's like a convolutional layer but from the other way around. So we are creating the same layers here but from the back. For this we are first resetting and reshaping our dense layer. We use 49 times 32 input dimensionality. So this is the dimensionality of the layer in line 22. So after flattening our last hidden convolutional layer, 32 filters times 49 features, we have a lot of of values, and here I just wrote it down. So if you change here the filters to, I don't know, 48 or so, please consider also to change this value and this one here in 27 accordingly. We are doing now creating our decoding layers here with the conf1d transpose layers. So it's like the same call as previously, but it's like the inverse convolutional layers for our data. So we are let's say we are entangling our dense neural network into some kind of convolutional representation. We're going here to 32 filters, 16 filters, and then finally with one filter, kernel size 1 convolutional layer, we are creating our final output layer in 42. And then we create our model, so with the Keras Models API, but also we are creating our encoder model, where the input is the input layer and the output is the bottleneck layer. So this is something we will use for our future videos. So we will return the model and the encoder model, but this is something we will not use today. And then of course, compiling the model, and as a loss function, we use some loss function from a regression problem, mean square error. So because we have a regression problem, but other loss functions also work. I think also cross entropy should also work, but with the MSE, I just want to underline that we are having a regression problem. So model summary, you see it here. We have our input layer 49 and 1, and then 16 filters 32. Then you see here 49 times 32, 1568. Then we have our bottleneck layer with two output, and then it goes back into this 1568 dense layer, which is like this one here, 49 times 32. And then we are doing some reshaping and then putting it back into our transpose convolutional layer, which finally leads to our original image, or not original image, but original spectrum here in this last layer. So in total, we have 14,000 parameters to train. We can do now some training. I will also use some kind of callback, the early stopping, so to monitor the validation loss with a patience of 5. So also here the verbose is at 0, so it will not return any history, but you can change it to 1 or 2, and then you get some output. So it's now done. And then we can also plot our loss function. Now you see there's, this looks a little bit broken. That's strange. Sometimes these things happen in Colab somehow. Then you have to redo the import of the matplotlib and also my styling, and then it works. But it's kind of strange. You see all the labels are missing. And there it is. So some kind of bug or so. I'm not sure 100%. And here you see the loss function from the training and testing. And then after the 5th epoch, it remains like a straight line almost. So probably it then reaches the overfitting region, and then it made some stopping at epoch number 30. Actually 31, it starts here at 0. So we set 500 in total. So it's only like 10% of the initial epochs have been used. Let's go to our signal reconstruction in our next cell. So what we're doing now is we are taking first our original signal. So it's like this X training scaled. We use some training. We can also use some the test data as well. I mean, as you like. And then we use some random spectrum. Here's the index value. I just picked up 5. You can also pick any other number. And then we have to reshape it and put it back in our scaler, where we do the inverse transformation. So this is the original signal. And the same thing needs to be applied for our reconstructed signal, where we do basically the same thing, but we are calling the model.predict and put our training scaled data into the prediction. So this is like the prediction of our model. So we can plot it here, of course, our original and reconstruct it. I didn't store the wavelength information, so I just simply call it spectra array index and then the normalized reflectance, and we can plot it. So let's take a look. And there you go. So this looks pretty nice. I mean, it's a little bit noisy here, and this spike here is this spike where all values have been normalized. So in all spectra, you will see this small spike here because neural network tried forcefully to return the value 1 all the time, but it somehow failed. And since our compression is 2-dimensional only, this is a good case, but there are way worse cases. So let's take here 15, for example. Yeah, this looks really bad. How does 16 look like? Well, this is again a little bit better, but here you see the spike again. And maybe 100 just to see. This looks also quite nice. Yeah. So you see, reconstruction is not perfect. It looks suitable, I would say, feasible for our next step. But yeah, we can live with that because, I mean, you have to consider that it's a 2-dimensional compression. So that's ridiculously, yeah, large compression, high compression. So that we were even able to reconstruct anything, it's kind of a miracle, I would say. So yeah, this is the part of this week's coding session with the autoencoders. I hope you enjoyed this video, also that it's a little bit shorter than the other times, and please let me know if it's enough for you to simply explain all the different cells, and then you can go with your own pace through the code, or whether I should do some live coding again. As you like, this is just another suggestion for my YouTube videos. Yeah, I hope you enjoyed today's session, guys, and hopefully we'll see each other next week where we will talk about the latent space. So we will use the latent vector to see how the classes look like. Until then, take care and see you next time.